So in this video, we're going to talk about what an exponential function is and what more specifically the graphs look like. So this would be our general format for a plain old exponential function. So the a value always gives us what we call our initial value, or if we're looking at the graph, this would be our y-intercept. Kind of like the b of a linear equation. The b value is really the thing that tells us how fast the function's growing or decreasing. So this is our rate of, we'll say, growth or decay, to use proper exponential function terminology. Okay, so the b value is what tells us whether the function's increasing or decreasing. We can tell by that number. So to be a little bit more specific, when the b value is something greater than 1, now keep in mind it cannot be greater than or equal to 1, because if b was 1, we would just have a plain flat line. So if b is greater than 1, this is going to give us an increasing function. And when we have that b is between 0 and 1, now again, the reason we have such specific constraints is that if b was negative, we would have a function that was alternating between being positive and negative. So it really has to be specifically between 0 and 1. This is going to give us a decreasing function. So let's look at the graphs of a few of these functions and we'll talk about what we can see. So here's a graph of an exponential function. So right off the bat, I can find my a value by, remember we said that's the initial value or the y-intercept. So if I find the point where this graph crosses the y-axis, then I know my a value. So a lot of times if you're asked to find a or determine a, then you can actually pull it right off the graph. B, we can't be as specific right now, but by the general shape of the graph, we know that since my function is increasing over time, it's generally going up, then I know that at least b is greater than 1. So I might not know the specific value, but I can describe it by saying it's greater than 1. Some other general interesting facts about this function, if you take a look at it and think about its domain, this function is going to go forever to the left, and it's going to go up, but getting a little bit wider forever. So our domain has no restrictions. So our domain, if we were using set builder notation, we'd say it's just the whole set of real numbers. The range, if you notice, I know it's hard to tell, I've drawn all over the graph, but exponential functions have what's called an asymptote on the x-axis, which means they get really, really close to the x-axis, but they never actually touch it. So when we're writing our range, we have to be careful and say that y is going to be greater than 0, but we cannot say greater than or equal because it actually won't ever touch the x-axis. So our range is just y greater than 0. This is also a one-to-one function because it passes the horizontal line test, meaning that no y's are repeated. So if I was to do a bunch of horizontal lines here, I'm good. So this is a one-to-one function. If we were asked if it's onto, since this function never goes and touches any of these y's down here, this is not onto. So it's a function that is one-to-one but not onto. Okay, let's look at another graph. Okay, kind of similar, still has the same general shape. However, this time I think you can probably tell that it's decreasing, which right away helps us tell something about our b. Remember we said that when it's a decreasing function, the b value is between 0 and 1. As far as the a value, if I go find the point where the function crosses the y-axis, I see that it's at 2. So my a value is 2. I don't think anything else is going to change. We're going to have the same domain, same range, still one-to-one, still not onto. So everything else we can just keep the same. Here's another exponential function. So I think you'll notice right away something's a little odd, right? It's almost as if the graph has been flipped. Now if you notice, our y-intercept this time is a negative number. Our a value is -4. And if you remember from geometry, when you negate the initial part of a function like that, it's going to flip it over the x-axis. So that's why this graph is doing this. So to get the b value, we have to sort of picture what it looked like before it was reflected. So if you can kind of picture, if I reflected this graph, it would be sort of going in a downward direction from left to right. So we really have to look at it in the top two quadrants to be able to tell. So that means that this b value must be between 0 and 1, because when it is reflected and put back into the top two quadrants, it's a decreasing function. Our domain is going to stay the same. Our range, however, is a little bit different. This time, all of our values, we still have that asymptote right here, but everything else is below the x-axis. So this time our range is very similar, but it's all values smaller than 0. Still not equal to 0. Still 1 to 1, still not onto. So the only thing that really changed was because of this negative, we had to sort of reflect the graph, and our range became all numbers less than 0 instead of greater than. Here's one last example. We still have that sort of negative trend because if you look, our y-intercept again is a negative number, which is why the graph has been flipped over the x-axis. So again, to figure out my b, let's try to picture what this would look like if I flipped it back up into the top 2 quadrants. And if we did that, we would have an increasing function, which means that b must be bigger than 1. Again, same things. Domain still the same. We're going to have that same range we had last time, with all y values being less than 0 because this graph is below the x-axis. Still 1 to 1, still not onto. So those are all of the classifying characteristics of the graph of an exponential function.